the first thing that we need to understand when we talk about carbohydrates certainly is the nomenclature of them and their structure. So the first thing that we learn about carbohydrates is they are typically named by their common names. The IUPAC names are a little bit too complicated, and when chemists were originally discovering them, they basically gave them common names to make it easier for them to remember. And so oftentimes this is one of the maybe largest hurdles for students, is to really understand the common names of all of the carbohydrates. For this class, I'm not going to have you memorize a lot of the common names. Certainly we're going to have to know some of the more typical common names of carbohydrates, such as that of glucose and fructose and ribose, and some of the smaller ones like glyceraldehyde. And as a matter of fact, when we think about the simplest carbohydrate, it is glyceraldehyde. So what does glyceraldehyde look like? Well, if we think about a three-carbon chain in which all three carbons have an alcohol coming off of them, this is called glycerol. So glycerol has that structure OH, CH2, CHOH, CH2OH. And glycerol is the backbone of a lot of fats. So fatty acids are derived from their triacylglycerides, where glycerol is the backbone of that glyceride. Now, the difference between glycerol and glyceraldehyde looks like this. So here is glyceraldehyde, and so glyceraldehyde, right? And if you look at the difference between these two structures, well, first of all, there's a lot of similarities. We see three-carbon chain, but we see an aldehyde functional group. And so this is often called an aldotriose because of the three carbons, but also because of the aldehyde functional group. So one of the alcohols has been converted into an aldehyde. It's been oxidized to an aldehyde. Now, notice in glycerol there is symmetry within the molecule, but in glyceraldehyde there is no symmetry. So the oxidation of one of the primary alcohols into an aldehyde essentially makes glyceraldehyde an unsymmetrical molecule, and therefore that central carbon there is a stereogenic carbon. And this is going to become very important, because when we think about carbohydrates, carbohydrates have one or more stereogenic carbons. And as a matter of fact, when the longer the chain gets, the more stereogenic carbons you get, the more stereoisomers you have possible. Now let's take a look at how we would typically draw glyceraldehyde, right, in the bond line formula. So this is the structure of glyceraldehyde, and I've highlighted that stereogenic carbon there, right? We have an aldehyde connected to a CHOH connected to a CH2OH. And so, of course, we can draw the two stereoisomers of it. We can draw the structure where that stereogenic hydrogen or OH group is coming out at me, and the hydrogen is going back. And if I figure out the absolute configuration of this molecule, right, the OH is the number one priority, the carbonyl is number 2, and then that CH2OH is number 3. So I'm rotating in a clockwise fashion, and therefore this is R. And of course I could also draw the enantiomer of this, which looks like this, where the OH is going back and the hydrogen is coming out at me. So I have these two stereoisomers of one another, R and S glyceraldehyde. So if you remember from the preview, I said that we're going to have to think about the Fischer projection. So a new projection. Obviously, this is the dash and wedge projection, we call them. But when we get into carbohydrate chemistry with all of its stereogenic centers, oftentimes it becomes much easier to draw what's called a Fischer projection. So let's take a look at how we draw Fischer projections. And I'm going to start by simply drawing the tetrahedral that stereogenic carbon, and I'm going to place the aldehyde on the top. I'm going to place the CH2OH group in the same plane, and then I'm going to place the OH coming out at me so that I have the R stereoisomer. So this is a simple representation of R glyceraldehyde that we've seen many times before. So hopefully you can understand that this is the R stereoisomer of glyceraldehyde. If you need to, go back and review your notes about stereochemistry, because that's definitely going to come up time and time again. All right, so now, what is a Fischer projection? So the way that we orient this tetrahedral carbon is essentially we're going to rotate it 90 degrees along that carbon aldehyde axis, so that the OH is still coming out at me, but now the hydrogen is also coming out at me, and the CH2OH is actually going behind me. And so when I do that, this is what I get. Remember, in terms of the perspective now, and of course this is a great time if you have a difficult time seeing things in 3 dimensions to get out your model kits. So envision the OH bond and the hydrogen bond, carbon-hydrogen bond, carbon-OH bond, are coming out at me, and the carbon aldehyde bond and the carbon CH2OH bond are going behind me. So this is the orientation that I have for a Fischer projection. Now what we do, so the key is that the horizontal lines, the carbon, hydrogen, and carbon OH bond, are coming out of the plane, and the vertical lines, right, the aldehyde to carbon to CH2OH, are actually going back, right? They're projecting backwards. To make this image more simple, what we do is we simply draw then horizontal lines and vertical lines, just like this. And we put the substituents on those at the end of those lines, and we simply omit the carbon in the center. So at the top we have the aldehyde, at the right we have an OH, at the bottom we have a CH2OH, and lastly at the left we have a hydrogen. And this is the Fischer projection of R glyceraldehyde. Now, obviously we can draw different types of Fischer projections of R glyceraldehyde depending on what is going back and what is coming out at us. But one thing to denote, to make things much simpler, especially as we get into more complex carbohydrates, is that it is always convention to place the most oxidized carbon, and in this particular case the most oxidized carbon is always going to be that aldehyde carbon on the top, right? So the aldehyde carbon always goes on the top. That's where when you're drawing a Fischer projection, you always orient the aldehyde carbon on the top. And that's going to be very important because obviously there are many ways to draw Fischer projections, but convention says that for carbohydrates, to make things easier for us, we always place the most oxidized carbon on the top. So I'm going to simply redraw that Fischer projection, and I want to talk a little bit more about convention. So so that stereogenic carbon at the bottom, closest to the CH2OH, is always what we call the configurational carbon. And as we're going to see, we're going to add more carbon OH bonds, and the carbohydrate chain is going to get longer. But the carbon at the base, the carbon at the bottom, the stereogenic carbon at the bottom, I should say, is always classified as the configurational carbon. Now, why is it called the configurational carbon? Because when so Fischer projections came about by a chemist by the name of Emil Fischer. And so he really kind of set the standard for conventions of carbohydrates. And when he was looking at R-glyceraldehyde, he noticed that R-glyceraldehyde happens to rotate plane polarized light, and it rotates it in a clockwise manner. So what did he do? Well, he said, okay, I'm going to label this then D-glyceraldehyde. Why D? Because it rotated light in a dextrorotatory manner. And so this kind of set the stage for all other carbohydrates. Because what he did was he said, oh, okay, well, in my Fischer projection, notice the OH is going to be on the right. So he labeled all sugars whose configurational carbon has the OH that's on the right-hand side as D. Now this is important to understand because as we learned last semester when talking about plane polarized light and how molecules rotate it, we know that it's essentially independent of the absolute configuration. So one molecule may be labeled R and it could rotate plane polarized light clockwise, and one might be labeled R and rotate plane polarized light counterclockwise, and so it doesn't matter. Well, Fischer labeled them all D, in which case the configurational carbon has the OH on the right, regardless of how they rotate light. So it's important to understand that when we talk about D, and of course then there's L, lever rotatory, those have nothing to do with how they rotate plane polarized light, except for glyceraldehyde. So it happens that glyceraldehyde, right? So here is the Fischer projection of glyceraldehyde. It's labeled D. It rotates plane polarized light clockwise, so we say it's plus, so we call this D plus glyceraldehyde. And of course, its enantiomer is this, right? So one of the beauties of Fischer projections is we can see the symmetry between two enantiomers. So it's very easy to tell two enantiomers of carbohydrates from one another because of the way that Fischer projections orient themselves. So essentially the mirror image of D would be the L stereoisomer. So this would be L minus glyceraldehyde. So keep in mind the D and the plus, the way it rotates plane polarized light, are independent of one another except for glyceraldehyde. And that's oftentimes really confusing. And as a matter of fact, many chemists for many years have said we should get rid of the D nomenclature altogether because it's very confusing for students, and rightly so. So glyceraldehyde obviously has one stereogenic center. It is an aldotriose, so there's 3 carbons. And of course we can extend the chain by 1 carbon and we can get to aldotetroses. So aldotetroses have 4 carbon chains, and there are 2 stereogenic centers. So we're going to see a pattern where the ends are always the same. You have an aldehyde functional group, the aldotetroses, and then you have a CH2OH at the bottom. And we're simply increasing the carbon chain by 1 carbon and adding water across, right? Because hydrates of carbon. So when you have 2 stereogenic centers, you have 4 possible stereoisomers, unless there is some type of symmetry, which we know that carbohydrates have no plane of symmetry in them, right? So the first one we're going to take a look at, we're going to start with this kind of backbone, right, where I've simply now, instead of having 1 line, I have 2 lines. Each line, now each horizontal line represents a carbon that is a stereogenic center. And I'm going to start with the OH at the bottom. That remember, that is called the configurational carbon. So I'm going to start with the configurational carbon where the OH is on the right hand side. So I know that this sugar is going to be D, whatever the name is, right? And so now I can put the other OH either on the right or on the left, right? So I'll put it on the right so they're on the same side. And this particular aldotetros is erythros. So we have D. Now it happens that when you take D-erythros and put it in plain polarized light, it rotates it counterclockwise. So it's minus erythros, D minus erythros. So right off the bat you can see that the way that carbohydrates rotate plain polarized light is independent of their designation D versus L. You can always tell the D designation simply by looking at the configurational carbon, that carbon on the bottom, the stereogenic carbon that's closest to the bottom. When the OH is on the right, it's D. When the OH is on the left, it is L. So this is D minus erythros. And of course, it has an enantiomer to it, which is the mirror image of it. And so I can draw that mirror image. Looks like this, right? So now the 2 OH groups are on the left-hand side, and since the configurational carbon has its OH group on the left-hand side, it is L-erythros, right? So we have D and L-erythros. And of course, now there's now I can have the 2 OH groups essentially be on opposite sides. So again, I'm going to start with the OH at my configurational carbon on the right-hand side. So I know this is going to be a D designation, right, based on Fischer designation. And of course, the OH at the top is going to be on the left-hand side. This sugar is called threose, D-threose. So we have erythros and we have threose for the aldotetroses. And of course, D-threose has an enantiomer to it, which is its mirror image, and it looks like this. And this is called L-threose. You have to, get used to the names. Erythros, threose for the aldotetroses. Erythros and threose. So these are all 4 of the stereoisomers of the aldotetroses. Now we move on to the aldopentoses. And as the name would imply, they are 5 carbon chains, and there are 3 stereogenic centers, and there are 8 stereoisomers. And so you see that now the complexity increases, just like always when we go from having multiple stereogenic centers. Obviously, I'm not going to draw all stereoisomers, but it's easy for me to draw at least 4 of them, which are all the D configurations based on that configurational carbon, right? So we start off where, again, the OH is on the right, and now I can put all of the other OHs on the same side of it, right? So this is D-ribose. D-ribose, very important sugar. in terms of nucleic acids, ribonucleic acids. So that's kind of a cool sugar. And then, of course, I can take now the OH on the top and put it on the left-hand side. So here's another sugar, right? So again, the configurational carbon is going to have the OH on the right, and I'm going to put the OH on the top on the left-hand side. So this is one other stereoisomer. It is called D-arabinose. So again, notice D-ribose, D-arabinose based on that configurational carbon. So now I can draw another one where the middle carbon has its OH on the left-hand side. So again, notice aldehyde on top, CH2OH on the bottom. The configurational carbon has its OH on the right. The middle carbon now has its OH on the left. And then I've put the top carbon with OH on the right. So this is D-xylose. And then lastly, I can put both of the top carbon OH groups on the left-hand side, keeping that configurational carbon with the OH on the right. And this is D-lysose, right? So these are the D stereoisomers, and of course each one of them has an enantiomer that is the L. So we have L-ribose, L-arabinose, L-xylose, and L-lysose, where the OH, that configurational carbon OH, is going to be on the left-hand side, and they're essentially going to be mirror images of one another. So if you know one, then obviously you know the other one. And of course, then we have the aldohexoses. The aldohexoses, 6 carbons, 4 stereogenic centers, which means there are 16 stereoisomers. Now, I'm not going to go through all 16. I'm not going to go through all 8 of them. What I want you to know is one of them very well. And it looks like this. So again, now we have 4 stereogenic centers. And at the top we have aldehyde, and at the bottom we have our CH2OH. We have an OH on the right. That configurational carbon means that this is a D sugar. And notice this pattern. So the if we're counting down the carbons from the aldehyde, 1, 2, 3, 4, 5. So the configurational carbon is carbon number 5. So carbon number 4 has the OH on the same side of it. Carbon number 3 has the OH on the left-hand side, and carbon number 2 has the OH on the right-hand side. So all of the OHs are on the right-hand side except for C3. C3 has the OH on the left-hand side. And this particular carbohydrate, maybe some of you have figured it out right now, it's one of the most popular carbohydrates for biochemical pathways. It is the carbohydrate that fuels our brains. It is D-glucose. Right? So this one we're going to see over and over again in terms of modifying it and doing chemistry with it and all sorts of things, right? Now we've talked about the aldoses. They're called aldoses: aldotriose, aldotetrose, aldopentose, aldohexoses. There also exist ketoses, so not aldoses but ketoses, which, as the name implies, there is, instead of an aldehyde, a ketone in it. And the most famous ketose has a structure that looks like this, right? Where notice if you count the carbons 1, 2, 3, 4, 5, 6. So this is a ketohexose, but in this situation, the C2 carbon is the oxidized carbon, and it's a ketone. So we have a CH2OH at the top, and then we have a ketone, followed by now only 3 stereogenic centers. So ketoses with the same number of carbons have less stereogenic centers than than aldoses do, right? In this particular one, notice again the configurational carbon is still, the OH is on the right hand side, so this is D, and this particular ketose is D-fructose. D-fructose. So that's important to understand. And that gives you a little bit about the nomenclature of carbohydrates, a brief little interlude about the nomenclature of carbohydrates.